All right, we're going to start talking about inertia and motion. These two concepts help us understand collisions. That's going to be kind of the end goal of this chapter is talking about collisions. So, what happens when two things collide?
They bounce off.
Right? Usually they bounce apart. Right? Two things collide, they bounce apart. Where do we see those types of collisions in everyday life? Car crash. Okay? Sometimes in a car crash, what happens though?
They stick.
They stick, right? That's a different type of collision. We're going to talk about both of those. Where else do we see just collisions in general?
Sports.
Okay, sports. What else? What types of games do we see collisions? Right, we talked about it a little bit
Jerks.
in our last chapter.
Like bumper cars?
Yeah, bumper cars. Yep.
Marbles. Bowling.
Yeah, marbles, bowling. Yep.
Baseball.
Pool. Yeah, baseball. Okay. All right, so those are types of things we'll see collisions. And when we see collisions, we have a transfer of what?
Energy.
Energy. Good. Okay, so that's going to kind of be how we tie those two chapters together. In collisions, we'll see maybe a perfect transfer of energy, which would be that one object hits another and completely transfers all of its energy. We talked about this with the cue ball situation, right? If you hit a cue ball in pool, right, you hit the white ball, there's a ball at rest. Theoretically, the cue ball should come to a stop because it should transfer all of its energy to that colored one, right? That would be what we call a perfect collision. And I'll just give you a name for that here in a second, but that would be a total transfer of kinetic energy. That'd be ideal. So we have two types of collisions we're going to talk about, not today, but I'm going to get there eventually. First of which is called elastic collisions. I think the names are counterintuitive, but elastic collisions are when they bounce apart, right? When two things collide and they rebound off of each other or they end up apart. Okay. In a perfectly elastic collision, we see what we consider a conservation of energy. So that's the cue ball situation that we were talking about. Right? If we have a perfectly elastic collision, that means no energy is lost. All of the energy is transferred from one object to another. Okay? It would be like if you're driving and you rear end somebody. You rear end somebody, they move, you stop. Right? That would be a perfectly elastic collision. Right? If they were at rest and you came to a rest. Okay? Opposite type of collision is called an inelastic collision, and this is when two objects collide and stick. They collide and stick. Can you think of some examples for this? We talked a little bit of kind of like a mangled car situation.
When you're making a pizza, 2 balls of dough.
Okay.
Yes.
Yes.
Just close your mouth.
That's right. That does work. Not a scenario I happen upon often, but it does work. Okay, what else? A magnet? Okay, good, yeah.
Throwing gum in a trash can.
Okay, yep. Did you guys ever have those paddles that you put on your hand with the Velcro ball, you know, right? Right, that's what I really think of with this, because when you throw the ball and it hits it, right, your hand will move a little bit. We'll see what happens in collisions like that. Because usually once those two objects come together, there's still a little motion, right, and that has to deal with the conservation of momentum. So, inelastic and elastic collisions, we'll talk a lot more about those tomorrow, but today we're going to focus on momentum. Okay, so momentum. The equation for momentum is mass times velocity. Momentum is for some reason given with a p. Has to deal with its Latin name. But the variable for momentum is p. Right? We can't use m because it already means mass. So p is the symbol or variable for momentum. What does the delta mean? Change in, right? Change in, final minus initial. So if I just wanted the momentum at one point in time, not a change in, it would just be P equals mv. Does that part make sense? You don't have to have the delta. The delta just means if we're looking at a before and an after. All right. Momentum is a vector quantity, which means it has to have
Direction.
good magnitude and direction. So it needs to have direction. It's one of those things where if we're given a cardinal direction, we should include it. And if we're not given a cardinal direction, then a positive, negative would be sufficient. Okay. Momentum, that vector has to be in the direction of the velocity, right? That's really, really straightforward. You don't have to write that part down, right? If you're traveling north, that should mean that your momentum is in the north, right? That is pretty self-explanatory. Okay, units for momentum are kilograms times meters per second. It's just literally the dimensional analysis from this equation. If we took 10 kilograms times 10 meters per second, our momentum would be 100 kilogram meters per second. Right? That's just taking the units. So there's not a fancy like shortened unit for this like we did with joules and newtons. It's just. All right, let's look at a couple here. If I have, you don't have to write these part down, let's just talk through it. A large truck and a small car are moving at the same speed. Which is more difficult to slow down, the truck or the car? Truck. Why? More mass, right? Greater amount of momentum means greater amount of inertia, which means more resistance to change, right? That should be a pretty self-explanatory, or at least kind of intuitive concept, right? The bigger the thing, the harder it is to slow down. It works in the opposite way as well, which would be harder to get started. If they're both at rest, which would be harder to put into motion. The truck also, right? Same type of thing, same resistance to change. Okay, let's try this one. A runner's traveling 3.21 meters per second west. The runner has a mass of 65. What's the momentum? It really is as easy as it seems.
What unit is momentum measured in?
Kilograms.
It was on the last slide. Kilograms times meters per second. There's no like fancy shortened unit. It's just that. I know. So there's no delta here. There's no need for us to put the delta because there's just one mass and one velocity. All right, we're not looking at a before and after. We just want to know how much momentum does he have right now. Yeah?
Yep.
Okay, good. Do this one on your own. A boulder is found to have momentum of that. If the velocity is 16.4, what's the mass? All right. 244.8. I think we're good with that, right? Okay, great. That's as easy as it gets. Now let's move one step further. An object's dropped from a height of 8.8 meters. What's the momentum after 1.2 seconds? What's the momentum after 1.2 seconds? So let's start looking at what we have. Okay, if I hadn't given you this clue, let's kind of look at how could we get there. Right, I'm given a mass. I'm given a height or a distance. I'm also given time. But I want to find momentum. Right? So my equation for momentum is m times v. I have this. I need that, so I've got to be able to solve for velocity. Can I solve for velocity from what I was given previously? Why not?
You don't have it.
Yeah, can I solve for it from all the other things I have? Yeah. All right. I know that technically my initial velocity is 0 because it was dropped. What kinematics equation can I use? I think I can use the first one. Yes?
A is 9.8.
Negative 9.8,
Yeah, then you
right? You can either use the third Or you can use the first. Or really, you can use the second. Doesn't really matter which one you use, I guess. No, we can't use second because we need a final velocity. Okay, so you can use either one. Let's see if we get them to come out the same. VF equals 0 plus negative 9.8 times 1.2. Negative 11.76. Okay. All right, now we're going to start looking at forces that put things in motion and how those apply to momentum. So anytime we change speed or change direction, which would then involve a change in momentum, there's got to be some force that has been applied. We're going to kind of change Newton's second law, not change, but kind of derive the equation for our force from Newton's second law. So Newton's second law usually reads force is equal to mass times acceleration. I just want you to watch through what's happening here, right? Newton's second law usually says net force equals mass times acceleration. Agreed? Right? That's what we learned back in chapter 4. Okay, when I look at the equation for acceleration, acceleration is usually change in velocity over change in time. Okay, so all I did here was substitute that. So now I've got force. You know what this means right here? I don't mean to throw you off.
No.
Sigma, it means sum of. So really all it's saying is net force equals m times delta v over delta t. And then what does this look like? What's m times v look like? Momentum. So now we can look at an equation that says the net force is equal to change in momentum over change in time. Okay. The net force can equal the change in momentum over change in time. I would put that on your equation sheet. Okay, so we took that right from Newton's second law. Okay, so let's go ahead and start looking at what we have. We have the mass. We have the, what's 52 here?
Velocity.
And its velocity what? Initial. Because it comes to a stop,
Yeah.
our velocity final is 0. Okay, and then we were also given time. So I have everything I need to be able to solve for my change in momentum, right? What was my change in momentum over that time? So delta P equals m times final velocity minus initial velocity over time. Force is given to us in newtons. Okay? Here it's really, really important that we did 0 minus 52. It's really going to be tempting for you to just plug in the velocity there, but it's final minus initial, so 0 minus that. Let's see. So my P, my momentum value was negative 11,033.04. I take that divided by my time. Oh man, okay. I did this a little bit backwards right here. This should be labeled force. Sorry about that. Okay, because this part was the delta P, this part was my T on the bottom. So that was my fault. So that negative 11,033, that is my force. There we go. Sorry about that. Okay, the delta P is just the numerator of that equation, and then when I divide it by time, that now gives me my force. Okay, and why is my force negative here? It's slowing it down, right? I was originally driving north, so the force that's bringing me to a stop has to be going south. So you could have labeled it 11,033 newtons, then just south. Okay, you don't have to put the negative, you could just put south if you wanted. All right. All right. Go ahead and try this one on your own. Newton is its weight. Right, divide by 9.8 to get that into mass.
What?
Do you have to put mass in?
Yeah. Yes, you do. Thank you. 5.61. Let's try it again. Is that what you had for mass? Did I do that part right? Okay, great. How about 4.8? There we go. Sorry about that.
4.8.
4.81. Did you divide the wrong way?
And then you have to add 14
Remember, when we have these triangle type equations and our variables on the bottom, we switch these two places. Right, so we're really taking 36 times 5.61, 201, divided by 42. All right, good. Thank you for catching that mass. I didn't mean to do that. All right. Now we're going to give the change in momentum a fancy name. Okay, that's called an impulse. Okay. All that impulse is the change in momentum. So delta P that we've been solving for, right? P is momentum. Delta P is for some reason called impulse. Okay? So we rearranged our previous equation to solve just impulse instead, right? Our equation used to look like this. Force equals delta P over delta T. All we did was rearrange. Right? So it doesn't change our equation at all. We just rearrange what the focus was, right? Anytime you solve for the change in momentum, that would be called impulse. Okay, you're welcome to rewrite this on your equation sheet, but it's really the same thing you just wrote on there, so that's up to you. Okay. All right. When we talk about impulse, we're talking about a change in momentum for any object that's involved in the collision or involved in the situation or whatever it is. Everything has a change in momentum during that time. Okay? Impulse is really good for looking at basically the exact moment of the switch, right? When two things collide and something changes direction or changes whatever, that's when we really look at impulse. Okay? But essentially, it's just the change in momentum. Okay? All right, we are going to be able to connect these two equations now. Here is one equation to solve for change momentum. Here's the other. When I have two equations set equal to the same thing, what can I do? I can set them equal to each other, right? It's just a substitution. So this is basically two different ways to solve for the change momentum set in the same equation. Okay, I would go ahead and put that one on your equation sheet. That way you've got all of those things in one place. Okay. So we could be looking at a momentum or an impulse problem and not even have momentum in the equation. Three seconds. Do we have to use our larger equation here? No. Can't we just do delta P equals F delta T? 64 times 3. Right. That's it. 192 kilogram meters per second. Okay, you might also see units that are Newton times seconds, right? Because when you take force times time, that's Newton times seconds. We'll still go ahead and just measure it like that. But if you see it that way, that's still a momentum unit as well. All right, I don't want to do that one right now. Let's try this one. So we have a force of 25, sorry. T equals 0.23. My velocity initial equals 0. Velocity final equals 1.29. Now I'm looking for mass. Alright, so nowhere in here does it tell us about momentum. Nowhere does it even mention impulse, nothing like that. But we have all the things we need to go into that equation. Right, so force times time equals mass times delta V. What'd you say?
Is that just like one extra math? I did like F net was delta Q.
That's fine. Works the same way. Right, did you get the same thing? Yeah.
Oh,